Okay, guys, welcome. Today we're going to talk about graphs. Okay, so we'll just start with a introduction video for graphs. Now, the motivation behind the idea of a graph is we're going to suppose that we want to prove that at a party where there's 51 people, there is always a person who knows an even number of people. Okay, now we'll assume that acquaintance is mutual, and of course, there may be people who aren't acquainted. Um, and there also might be people who don't know anybody else. They might just be showing up to the party but don't know anybody. Now, this would be a tedious problem to work out if we were to try to list all of the different scenarios. But one thing that we can do is we can use sort of a graphical illustration to help. Now, let's just start this with a small sample for now first. So we're going to suppose that we try this for just 5 people instead. And just so that we can use the first 5 letters of the alphabet, we're going to name these 5 people: Alice, Bob, Carl, Diane, and Eve. Okay. Now we're going to suppose that when they first meet, that Alice knows everybody else, that Bob and Carl know each other, and that Carl also knows Eve. Okay. So if we were to list what we have here, we have that Alice knows 4 people, Bob knows 2, Carl knows 3, Diane knows 1, and Eve knows 2. Now, to see this graphically, we can represent each person by a small circle and then draw a line connecting them if they know each other, right? So something like this, right? So of course, A stands for Alice, B for Bob, C for Carl, D for Diane, and E for Eve, right? So for example, this line that connects A and B symbolizes the fact that Alice and Bob know each other, for example. Now, when we represent a sort of a relationship in this way, we call this a graph, right? So to be a little bit more precise, a graph consists of a set of nodes, which are those small circles, and sometimes we'll refer to them as points or vertices, but these are indicated by small circles. And then, of course, some, and of course, not necessarily all, and not necessarily even any. You could also have a graph that is just a bunch of nodes with no edges between them. But some of these nodes will be connected by edges, right, which are just symbolized or indicated by lines. Now, one thing that is also true is that the edges can be straight or curved, right? In this graph that we had here, all of the edges were straight, but there's nothing saying that I couldn't have drawn the graph like this. So I call this A, this B, this C, this D, and this E. I could have also done something like this, right? And the most common reason that we do something like this is so the edges don't intersect each other, but I could have done something that looks maybe like this. Right? Both of those would be the same graph, right? Okay. Now, the sets of nodes of a graph G is usually denoted by a capital letter V, right, for vertices. And we consider the set of edges by a capital E, right? So a frequent notation that you'll see is we'll call a graph G is equal to almost like an ordered pair V comma E. And then that will, of course, indicate that the graph G is made up of the nodes belonging to the set V and edges belonging to the set E. Now, when it comes to graph edges, the only thing that is relevant is the 2 nodes that they connect, right? So in other words, we consider edges almost as a 2-element subset of V, right? So if an edge connects U and V, this edge is the set U and V because it's joining those 2 together. And a lot of times we'll even drop the brackets and we'll just call an edge, for example, UV, if it connects the 2 nodes U and V. Now, a couple other sort of special things that you might see are if we allow if we allow 2 edges to connect the same pair of nodes, we call these parallel edges, right? So, for example, if you have something like 2 nodes and you have an edge here and an edge here, those would be considered parallel edges because they're connecting the same nodes. Now, if you allow an edge to connect a node to itself, we call this edge a loop. So for example, that would look, if you had maybe something like this loop right here, well, this edge here would be called a loop, right? Because it's connecting it to itself. Now, if we don't allow either of these two, we refer to the graph as a simple graph, right? So if there's no loops and there's no parallel edges, we refer to it as a simple graph. Now, if two nodes are connected by an edge, they are considered adjacent, and sometimes we'll even call them, oh yeah, it says it in the next thing. Nodes that are adjacent to a given node are called its neighbors, right? So just a bunch of terminology here. Now, the number of edges that, that leave a node is called the degree of the node, right? So for example, if you have something like this, let's just draw a simple graph over here. Maybe something like this, then we would say that the degree of this node, of course, is 1, as is this one, and this degree is 2. Right, so all based on the number of edges that are leaving a particular node. Now, we're going to return to a modified version of our problem at the beginning. Now, we're going to assume that the number 51 that we started with has no sort of special significance, and we're going to just say at a party with an odd number of people, right? And we want to prove that there's always a person who knows an even number of others. So instead of 51, we're just now saying for any odd number. Now, of course, we can use a graph theory idea to sort of represent this idea, right? So if we represent people with nodes and acquaintances with edges, then what we want to prove is that if a graph has an odd number of nodes, then does it have a node, at least one node with even degree? All right, so we're going to draw some examples, right, and just get an idea of what's going on. Right, so all of these graphs have odd degree number of nodes, right? And what I've done here is I've indicated the nodes with even degree by a hollow circle, or sorry, by a solid circle, so that means that it's even degree. And then an open circle would represent odd degree. So if we look at our first one, we have 5 nodes, all have degree 2. Right, then another graph with 5 nodes, if we connect if we were to add 2 edges here. Okay, let me just leave it. That'd probably be easier. Right, if we were to sort of connect those 2 edges, then we would get 5 nodes now have 1 with degree 2 and 4 with degree 3. Right, and of course, this was the graph that we drew earlier. It will have 1 node of degree 2 and 2 of degree 1. And then sort of this star figure here has 7 nodes, and they're all of degree 2. Right, and then of course here we have 5 nodes, 3 of degree 2, 2 of degree 1. And now here we have sort of this disconnected graph, which we'll talk about a little bit later, which has 7 nodes, 3 with degree 2, 2 with degree 1, and 2 with degree 3. So it looks like for these examples that we've drawn, it looks like it is true that if we have an odd number of nodes, we will have at least 1 node with even degree. Right? Now, what we're actually going to do is we're going to prove a stronger statement. Right? We're going to prove that if a graph has an odd number of nodes, then the number of nodes with even degree is also odd. Okay, so let's look at some graphs with even numbers of nodes. Right, and maybe we can formulate something even stronger. Right, so with 4 nodes, we have 2 degree 2 vertices and 2 degree 3 vertices based on this graph. And here we have 6 nodes, 3 with degree 1, 1 with degree 4, and 2 with degree 3. right? So just to highlight the pattern here, let me go back actually and say, right, so these had 5 odd degrees. Sorry, this had, we want to, oh, even degrees, so 5 even. This has 4, sorry, 1 even. This has 1 even. This has 7 even. This has 3 even. And this one has 3 even. Right? So it looks like all of these graphs with odd number of vertices all have an odd number of vertices with even degree. All right, that's what I want to highlight. And now here it looks like for 4 nodes, we have 2 that are even. For this 6 node graph, we have, let's see, so we have 3 that are degree 2 and 1 that's degree 1, sorry, degree 4. So we have 4 even. And then for this 4 node graph, they all have degree 3, so this has 0 even. Okay, and then for 6 nodes, they're all degree 2, so this is all 6 even. 2 nodes, both degree 0, so there are, I guess, 2 even, right? We consider 0 to be even. And then for 4 nodes, we have all degree 2, so this is 4 even. All right, so it looks like we can actually say that we can, for the even ones, if a graph has an even number of nodes, then the number of nodes with even degree is even. Okay. So it looks like we can formulate the following. We can say that in every graph, the number of nodes with odd degree is even, right? So if we go back and we look at our odd degree ones, we come back here, it looks like they're all even, right? Because now this would indicate that we have 0 odd. This would mean that we have, let's see, we would have 4 odd. We have 2 odd, 0 odd. Here we have 2 odd. And here we have, let's see, 4 odd. Okay, so it looks like in any graph, the number of nodes with odd degree is even, right? At least just based off of what we've conjectured. And now one way we can check it is we're going to build up a graph one edge at a time for an odd set of nodes, right? So we're going to look at 5 nodes. Now, if we have 0 edges, they're all degree 0, right? So that's this graph right here. Now, if we add a single edge, we're now going to have 3 that are degree 0 and 2 that are degree 1, right? So far, this is still holding, right? The number of odd nodes here is 5 odd and 0 even. Here we have 2 odd and 3 even. If we add another edge, it looks like we're going to get 4 odd and 1 even. Then for adding another edge, we're now going to have an, let's see, so we have 1 even and 4 odd. For adding another edge, it looks like we're going to have 1 even, 4 odd again. Here we're going to have 3 even, and 2 odd. And here it looks like we have 3 even, 2 odd. So it looks like for the examples that we did, it looks like this theorem is going to hold true, right? But of course, we want to prove this for any. So now with these ones that we've drawn out, we might notice that if you have both endpoints of a new edge have even degree, then you're increasing the number of nodes with odd degree by 2, right? So for example, if you have two nodes that have even degree, and we add a new edge in here, then these two even became two odds, right? So then you're increasing the number of nodes with odd degree by 2 in that scenario. Now, if both endpoints of a new edge have odd degree, and we connect them, then both of those odds are now even, and we now decrease the number of nodes with odd degree by 2. Now, if one is even and one's odd, and we connect them, then we don't change because the odd one became even and the even one became odd, so we're not changing the number of nodes with odd degree. So now essentially this is going to prove it because now you can just do this by induction, right? So if you have, if you were to just take, for example, a subset of two nodes, right, and consider all three of these cases, that would cover any graph that you could look at. Right. Now, since we've proven this theorem, we've proven that for any graph, the number of nodes with odd degree is even. This paves the way for a nice, powerful result, and this is known as the degree sum formula. And this says that the sum of the degrees of all your vertices for a particular graph is 2 times the number of edges, right? So, of course, that's going to tell you that the sum of the degrees should be even in order for a graph to exist. So for example, is there a graph on 6 nodes with 6 degrees? Or sorry, with these degrees? Well, if I add these, right, so we have 2 plus 5 times 3, so that's going to be 17. And of course, this cannot equal 2 times the number of edges, so the answer here, of course, is no. And then for part B, it's similar. If we add these together, I believe here we'll get a 15, which again is also odd, and it can't equal 2 times the number of edges, so this is also no. Right, okay, yeah, and then it's worked out here as well. Now, a follow-up example, if G is a graph with degree sequence 8, 5, 5, 4, 4, 4, 4, and then it looks like we have 8 2s, how many edges does G have? Well, if these are all the degrees, we need to add these together. And if we add them together, we get 42, right? And then, of course, that equals 2 times the number of edges. So the number of edges that we have is 21. Right, so that's an example that utilizes the degree sum formula. Okay, so that concludes this video on Introduction to Graphs. I hope you enjoyed, and I will see you next time.